Today our objective is still simplifying exponential expressions with properties of positive, negative, zero, and integer exponents. So to think about what we did in our previous lesson, we want to simplify the 4 expressions, and then we're going to check our results. So if we look at our first expression, z to the third times z to the fifth, again, thinking about the definition of the exponent, it tells us how many of the base that we're working with. Z to the third means we have 3 z's being multiplied together, and z to the fifth means we have 5 z's being multiplied together. So in total, how many z's do we have? That would be z to the 8th. Now, depending on the technology that you're using, if you're not able to do the exponent like you would writing by hand, oftentimes we use the caret key to represent exponents based on a base. So we could write z to the 8th this way, showing that the exponent is 8 using the caret key. So on your keyboard, if you hit Shift 6, you would get that icon. For number 2, we have d squared raised to the 4th power. So again, we have 4 of the quantity being multiplied together. So what does that mean for us? Well, we have 4 d squareds being multiplied together. And remember, d squared, or d to the second, means that you have 2 d's being multiplied together. Well, if you have 2 and 2 and 2 and 2, you have a total of 8 d's being multiplied together. So we could represent that as d to the 8th. For our third one, we have 2x to the third times 7x to the 14th. So remember, the exponent in the first term only belongs to the 3, and the exponent of 14 only belongs to the x. And again, I should have said the 3 only belongs to the x here. So what does that mean? Well, we have 2 times 7, which we know is 14, and x to the third means we have 3 x's being multiplied together, and x to the 14th means we have 14 x's being multiplied together. So how many x's in total do we have? Well, we have 17 x's. So we could write this as 14 times x to the 17th power. For number 4, we have the quantity 4x to the third squared times 3x to the 5th. So again, thinking about definitions and meanings. The power of 2 belongs to the quantity, so we have 2 sets of 4x to the thirds being multiplied out. And then we've got 3 times x to the 5th. Well, we could take our coefficients of the 2 4's and the 3 and multiply those together. And then x to the third, that means you have 3 x's multiplied together here. We have 3 others here, so right now we've got 6 x's, and then x to the 5th means we have 5 x's. So we have a total of 11 x's being multiplied together. So we could have x to the 11th, and then we know 16 times 3 gives us 48. So our simplified expression would be 48x to the 11th. And again, if you're using technology to represent your answer to show the 11 is the exponent, you can use the caret key to represent it that way. So let's continue thinking about the meanings of exponents and try simplifying some more expressions. So here we have a to the 5th divided by a to the 2nd. Well, what does that mean? A to the 5th means we have 5 a's being multiplied together, and a to the 2nd means we have 2 a's being multiplied together. So let's write those out. Now, notice we have a numerator and we have a denominator. Just like we've been doing all along, we've been dividing out greatest common factors to simplify, especially when we've been doing our slopes. So we do have some greatest common factors. We have a greatest common factor of a. In fact, we have 2 of them that we could divide out. So if we divide out those 2 greatest common factors of a, what are we left with? Well, we're left with 3 a's being multiplied together in the numerator. Well, how would you represent that? That means a to the third. So if we look at our second expression, we've got b to the 4th divided by b to the 3rd. What does that mean? Well, b to the fourth means we have 4 b's being multiplied together in the numerator, and b to the third means we have 3 b's being multiplied together in the denominator. Again, since it's division, do we have any greatest common factors we can divide out? B. In fact, we have 3 sets of b's we could divide out. So if we divide out those 3 sets of b's, what are we left with? We're left with 1 b in the numerator. So this simplifies to just b. Our third expression, we have x to the second, y to the sixth, divided by xy to the third. So thinking about the meanings, x to the second means 2 x's are being multiplied together, y to the sixth, 6 y's are being multiplied together. All of that is in the numerator. In our denominator, we have a single x. Remember, there's a power of 1 there. And y to the third, we have 3 y's being multiplied together. So we wrote it out based on the meaning. And again, we're dividing, so we're going to say, do we have any greatest common factors we could divide out? We can see we have a greatest common factor of x, and we also have the greatest common factor of y. In fact, we can divide out 3 pairs of greatest common factors of y's. So what are we left with? We're left with a single x and 3 y's being multiplied together in the numerator. So how can we write that as an expression? That would be x y to the third. So, did you notice a pattern when we were dividing with our exponents? When we're dividing, we're looking for the greatest common factors. And so, when we're dividing, notice what happened. We had a to the fifth over a to the second. We ended up with a to the third. B to the fourth divided by b to the third ended up being b. X to the second, y to the sixth divided by x, y to the third ended up being x, y to the third. The pattern is by dividing out those greatest common factors, you were in fact subtracting the exponents of the same base. And again, the base has to be a number other than 0 in order for it to be an exponential expression. And especially because we're talking about division, remember we're relating this back to slopes, we can't divide by 0. So we're being very specific here, saying that the base cannot be 0. It has to be a non-zero value. Let's take a look at a few other examples. Let's write out the meaning for each term and simplify and see if any patterns result. So the first one is 1/2 to the power of 3, or 1/2 cubed. Well, what does that mean? Well, think about this just like our other one. We have 1 as our base in the numerator and 2 as our base in the denominator. And this 3 says you have 3 sets of those. So let's write it out. We have 3 sets of 1 in the numerator and 3 sets of 2 in the denominator. And again, we look to see, are there any greatest common factors that we can divide out? In this case, we don't. So what happens? 1 times 1 times 1 is 1. 2 times 2 is 4, times 2 again is 8. So this can simplify to 1/8. Let's take a look at our part for b. Here we have the quantity y over z squared cubed, or to the third power. Well, again, what's the meaning? Well, we have 3 sets of what's on the inside of our quantity. So 3 sets of the numerator and 3 sets of the denominator. And again, we're going to look to see, is there any simplifying we can do, dividing out greatest common factors from the numerator and denominator? In this case, we do not. So what will we have? We've got y times y times y. Well, that's y to the third. And z squared times z squared times z squared. Well, if I have 2 z's here and 2 z's here, so far we're up to 4, and 2 z's here, we're up to 6, that's z to the 6th. So we've got y to the third, z to the 6th. So for our third example, we've got g squared divided by b to the third, and all of that is being squared, or raised to the second power. So what does that mean? That means we've got 2 sets of the insides, so 2 sets of the numerator and 2 sets of the denominator. So let's write that out. And let's see, is there any greatest common factors we can divide out because we've got that division there? There isn't, so let's see, let's simplify the numerator. Well, g squared, that means there's 2 g's here and 2 g's here, so a total of 4 g's in the numerator. b to the third means we have 3b's here and 3b's here, so we have a total of 6 in the denominator. So we got g to the fourth divided by b to the sixth. As we were working on writing out the meaning and simplifying, did you notice any patterns from when you had a fraction raised to an exponent? Or if you think about it as a division problem raised to an exponent. Hopefully you noticed that when we had this pattern resulting of something that was being divided by or as a fraction raised to an exponent, it was applied evenly to both the numerator and the denominator. So we're taking that exponent and applying it to the numerator and the denominator, showing the number of sets. And again, the bases have to be a number other than 0. So let's try taking what we've learned from yesterday and today and putting it all together, working on simplifying some exponential expressions. Let's give you a moment and try simplifying these two expressions and we'll check your results. The first one is x to the fifth divided by x to the third. Well, what does that mean? Well, that means we have 5 x's being multiplied in the numerator and 3 in the denominator. And because it's written as a ratio, the division problem, we're going to look for greatest common factors to divide out. We have greatest common factors of x's we can divide out. In fact, we've got 3 pairs we can divide out. So what are we left with? 2 x's in the numerator. Well, we know x times x can be written as x squared. Our second expression, x to the 28th divided by x to the 24th, well, what does that mean? We have 28 x's in our numerator and 24 x's in the denominator. Do we have any greatest common factors we can divide out? Yes, we do. We can see that we have x. In fact, we have 24 pairs of x's that we could divide out. So what would we be left with? We have 4 x's in the numerator. Well, how could we write that? That would be represented as x to the fourth. How about these expressions? What could they simplify to? Well, our first expression, 14x to the seventh divided by 2x to the third, means we've got 14 and then 7 x's being multiplied together. In our denominator, 2x to the third means we've got 2 and then 3 x's being multiplied together. We're looking to see if we have any greatest common factors we can divide out. Now we know that we can write 14 as 2 times 7, which means we have a greatest common factor now of 2 that we could divide out. We also have a greatest common factor of x that we can divide out. In fact, we have 3 pairs that we could divide out. So what would we be left with? We would have 7 times x to the fourth. Our second expression, 18 m to the 11th n to the 7th divided by 6m to the 4th. By meaning, we could write those out as our numerator and our denominator. And we're looking to see, do they have any greatest common factors we can divide out? Well, 18 we know comes from 3 times 6. So now we have a greatest common factor of 6 we could divide out. We see that we have a greatest common factor of m. In fact, we can divide out 4 pairs of m's, but no greatest common factor of n's. We're going to leave those as is. So let's divide out what we talked about and see what remains. In our numerator, we have 3, and then we have 7 m's and 7 n's. So our expression simplifies to 3m to the 7th n to the 7th. Here's 2 more expressions. Let's see if we can simplify those. Our first expression, x to the 14th times x to the 3rd, divided by x to the 9th. We have 14 x's and 3 more x's. So we have a total of 17 x's in our numerator and 9 x's in the denominator. Do we have any greatest common factors we could divide out? Yes, x. In fact, we have 9 pairs of x's for greatest common factors we could divide out, which would leave us with 8 x's in the numerator. So we can write that as x to the 8th. Our second expression of 2/3 to the 4th power. Well, think about the meaning. It's 4 sets of what's inside. 4 sets of the numerator and 4 sets of the denominator. And let's see if we can do any simplifying. So as of right now, we don't have any greatest common factors we could divide out, but we can simplify 2 times 2 times 2 times 2 as 2 to the 4th over 3 to the 4th, and they each have a value. 2 times 2 is 4, so 4 times 4 is 16, and 3 times 3 is 9, so 9 times 9 is 81. So we could write this as 16/81. Let's try 2 more. Can you simplify these expressions? Thinking of the meaning on the left, a to the 4th divided by 2ab squared, all raised to the 2nd power. We have 2 sets of the inside, so I'm going to write what's on the inside twice, in the numerator and the denominator. And then I'm going to look for greatest common factors I can divide out. And I can see I have a's I can divide out. In fact, let's think about what kind of a's we could divide out. If I have 4 here and 4 here, there's a total of 8. I have 8 a's in the numerators and 2 a's in the denominator, which means I have 2 pairs of a's I can divide out, which would leave me with 6 a's in the numerator. I don't have any greatest common factors of b in the numerator and both the denominator to divide out, nor do I have 2's, so those will remain. So we have a to the 6th over 4b to the 4th. Our second expression, we had 3 sets of the inside. And so we're looking for greatest common factors to divide out. So I can see clearly I have some x's, but how many could I do? So let's try cleaning this up a little bit. So 2 times 2 times 2 is 8, and 3 times 3 times 3 is 27. If I have 4 x's being multiplied together, and I have 3 sets of those, it's a total of 12. And if I had 3 sets of x squareds multiplied together, that's x to the 6th. So x to the 12th in the numerator, x to the 6th in the denominator means we have 6 greatest common factors of x's to divide out. So I'd be left with 6 x's in the numerator, and unfortunately no greatest common factor of y's to divide out, so those will all remain in the denominator. And 3 sets of 5 are 15. Therefore, we have 8 x to the 6th over 27 y to the 15th. So to recap the patterns that we saw today, when dividing exponents, we ended up subtracting the exponents of the same base because we were dividing out those greatest common factors. When you have a fraction raised to an exponent, remember it's still like we talked about before, saying the exponent is how many of the inside that you have. So even if it's written as a fraction, it's the same set saying we're applying this to the numerator and the denominator, and we're going to look to see if we can divide out any greatest common factors that exist between the two. So it's going to be your turn to add these to your repertoire and work on simplifying some more exponential expressions based on the patterns that we've seen.